Exam 3 is Wednesday, the 29th. And it covers everything up through linkages. I know that's not how you spell through. And the homework is due on Wednesday. But I'm behind on homework, so if Friday would be better or the next Monday would be better, those are both fine with me too. Okay, anybody have any questions about homework or test related things? Anybody have it? Aaron? Oh. Oh. Okay. Good job, Coraline. 16. Okay. Yeah, okay. So that's 17, right? Oh, it's part B? Okay. Um, 16. So when you add, so once the pulley has a moment of inertia, you can't assume that the tension's the same everywhere in that cable. And so free body diagram of the mass is a weight of 50 times 9.81, so 490.5. And then this is no longer 600. This is just some T. We don't know what it is. The Newton's second law says zero T plus the weight is equal to 50 times 0A. So we have one useful equation, T minus 50A is equal to 490.5. Well, that mass, so we will treat the pulley as a rigid body, but the mass we don't have to. It doesn't add anything to us for us to treat that as a rigid body because the orientation doesn't matter. Okay, and then free body diagram of the pulley. This one is a rigid body. Well, this is a rigid body, so let's go through the steps. So first, does the pulley have a fixed point? And so the about point is the center. Well, sort of lucky in this case. Well, it's not a big deal, but we don't have to use parallel axis theorem because the fixed point is the center of mass. And so the moment of inertia about the center of mass is it 1/2 times the mass times the radius squared for a disk? And you have to think about whether this disk is flipping like a paddle or a blade. Yep. Yeah, skip it still. As long as you have a fixed point, you're not going to need Newton's second law most likely. So just skip it. You can come back to it later if you need it. So 1/2 times 50. The radius is 0.1. Oh, that's not 50. That mass is 3. 0.1 squared. And so you get 0.015. Yes. Not about you getting it wrong, about me getting it right. Yeah, take that, Aaron. Been waiting to take Aaron down a peg. I will later. Oh, I can't talk about that here. Yeah, exactly. You didn't hear that. I'm editing that out of the video. And then free body diagram. There's the force in the middle. I'll call that R. That's the force the ground applies to that pin. And then we have this force T down. And then over here, it doesn't matter what that angle is. I suppose you could draw it like this. All we want is the moment that that produces. And if you notice that the cable is always perpendicular to the row vector, then it's just always going to be the length of the row vector times this, the magnitude of this force, no matter what angle that's at. This is 600. And so yeah, this is number 16 on rigid bodies. So the row vector for T is 0.10. The force is 0, negative T. The moment is negative 0.1 T. The row vector for the reaction force is 0. So there's no moment. And then the row vector for the 600 is negative 0.10. 0, negative 600, 60. No Newton's second law because we have a fixed point. Rotational equation says negative 0.1 T plus 60 is equal to 0.015 alpha. And so the second useful equation says negative 0.1 T minus 0.015 alpha is equal to negative 60. That's right.
So it could be all the way negative x direction.
Yeah, negative x. Yes, it could. The reason is cross product between two perpendicular vectors is just their magnitudes, you know, and so the perpendicular vectors here are no matter where this is, the force vector is perpendicular to the row vector. Can you picture that? So when you take the cross product, you get the same magnitude.
Constant ratio.
Mm-hmm. So yeah, it has to do with the perpendicular thing. I mean, you know, the cross product, one way to calculate cross product is magnitude of A times magnitude of B times the sine of the angle between them. So if they're perpendicular to each other, sine is just 1. Okay, so now we have two equations and how many variables? T, A, and alpha. And so now we have to relate A to alpha. So we need one constraint equation. And that is that the acceleration vector of the mass is equal to the tangential acceleration of the contact point on the pulley. Yeah, one term, but not the other. Okay. So this is the point that we're talking about on the pulley. So the acceleration of the mass, we have it as 0a. The acceleration of that, let me label it p. The acceleration of p, if we're only looking at the tangential part, is equal to alpha cross r. This is the centripetal part. And you can remember that. The way to remember which is if you remember the formulas that you learned in physics 1. Your formula for tangential acceleration was alpha times r, and your formula for centripetal was omega squared times r. So you can see that these are just vector versions of those equations. You could also, if you could multiply them out and see what direction they face. One's going to face tangent to the circle, and one's going to point towards the center of the circle. So we have this, our constraint equation, triple star, says 0a, I guess I'll make it 3D because of the cross products and stuff, is equal to 0, 0 alpha crossed with the r vector, which points from the center of the circular motion of this point P to the point P. So that's positive 0.1, 0, 0. And that says 0a is equal to 0, positive 0.1 alpha. Yes?
So that A, do we assume that the tension force, the tension of the box is 490. So you know that
we don't know that tension. I chose that A to be positive because if it's negative, that'll come out. Once you pin it down to a single component, the direction along that axis will work itself out. Well, this isn't really the equation. This is the equation. Star, star, star. A minus 0.1 alpha is equal to 0. And then you have 3 equations, 3 unknowns, and you can solve it. And you should get something a little less than the acceleration in the case where that thing doesn't have a moment of inertia. So if it's not somewhere in the same ballpark, something went wrong in this case. Any other questions about that one? Yeah. Yeah, so always all through physics 1 and up until now up until this stuff in dynamics, anytime a cable goes over nothing but pulleys, the tension is the same everywhere. That just changes when the pulleys are, so that's assuming massless and frictionless pulleys. If you have friction in the pulley, or if you have mass and dimensions to the pulley, then you can't assume that anymore. We have not done friction, although friction is super, it arises in a boring way. The friction just introduces some couple. So it's just an additive thing, you know. Yeah. Belt friction. Yes, it just adds a couple. That's right. No, actually, the way you calculate belt friction, now that I think about it, it gives you a ratio of the tensions on the 2 sides of the thing. So yeah, I guess it's not really done as a moment. Any other questions about that one? Any other homework questions? Yeah. Yeah. Yeah, I meant to sign it on Wednesday.
Okay, so I was looking at it. And I have no.
Okay. You have that one? Anybody?
Okay, so much information. Give one letter. Okay. It's literally gorgeous. What do you have? What do you have on your cell phone?
LTE, I'm just connect to the Wi-Fi. Yeah, that's what I do.
Do you charge that phone with a banana?
Like,
Um,
You guys see how a phone charger on a phone?
no.
You just voltage divider because the graphite is one with an insulator.
Mhm.
And then for your application, you can cool.
That is cool.
Yeah. I mean, it's kind of dangerous.
Yeah, anything cool is dangerous. Like parkour. Parkour is an example of something that's cool and dangerous. Were you here for the the gun safety day? Yeah, I don't know how not to get shot at community college. That's what it was about. It was like one of those. You've been to those before, haven't you? The like active shooter drills where we practice being quiet. It was one of those. Oh, okay. And we were watching parkour videos. Okay, linkages. Number 5. You have a pin joint on the wall on the left, and this is supposed to be horizontal. And then another one connected there has a pin and slot joint with the ground. The horizontal member is 2 meters long, 100 kilograms. Wow, that's big. So M1 is 100 kilograms. L1 is 2 meters. And the other member has a mass of 50 kilograms. And L2 is 1 meter. At the instant shown, neither member has any angular velocity. That's nice. No omegas. At this instant. Who can think of how that's going to come up in any way? Yes, watermelon equation at the end, when you're working on those constraints, it means you're not going to have the messy term in the watermelon equations. Neither member has angular velocity. What's the acceleration vector of this point here? I'll call that B. Okay, so first you'll isolate the two bodies. Let me know if you, I think this is probably enough to help you get going on this. You know, member 1, you'll do that rigid body analysis. How many useful equations are you going to get out of body 1? 1. Because it has a fixed point and so you won't need Newton's second law. So the only useful equation is going to be rotational. And then number 2, do the rigid body analysis. How many useful equations are you going to get out of that? 3, because that one doesn't have a fixed point. So at this point, we'll have 4 equations. How many unknowns are we going to have? This is a harder question. Because technically, if the endpoints are inclusive. 7, yeah, that's right. And the way that you know that, so 7 variables, is that you know you're going to, you know you're going to have 2 constraint equations saying that the acceleration here has to agree for the 2 members. They're connected. And then this one, the only constraint here says that there can't be any vertical acceleration. It can accelerate back and forth in that slot and just can't jump out of that slot. Okay.
So 2 from point B and 1 from C.
Yes. So let's just go through the constraint equations. Yeah. From the, yes, but the thing is, when you have a fixed joint, when you have a fixed point, there is almost always a reaction force there. Maybe I'd even say always there's a reaction force there that does not appear in the equations. And the reason it doesn't appear in the equations is because your about point is that fixed point, and you're only using the rotational. Yep. So we need, 3 constraint equations. All this stuff is a lot to just, little by little, all those kind of connections make sense, but it's a lot to remember, Yeah. Yeah. Yes. Okay, so first let's do the constraint at B. So I'll first do it for member 1. The acceleration of B is equal to alpha of 1 crossed with the r vector that goes from the center of the circular motion toward B. So I'll write that as 2B from, what did I call that, A? The fixed point? Yep. And then plus omega cross dot dot, that's all 0 because it was specified that there's no angular velocity at that point. That's 0, 0, alpha 1 crossed with the r vector 2b from A is 2, 0, 0. And so that is 0, 2 alpha 1. I guess I'll write that as 0. And then member 2, that one doesn't have a fixed point. So we're going to have to calculate the acceleration of B using relative motion. Acceleration of B relative to G is equal to the acceleration of B relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. This is the thing that we would have called, we already have a variable from Newton's laws if we would have gone through it all. And this is circular motion around the center of mass of 2. So AB relative to G is equal to 0, 0, alpha 2 crossed with the R vector that goes from the center of that member to B. So if I was like doing this physics problem at the disco, at what moment would I be correctly which instant am I correctly pointing in the direction of R? Yeah. Because it's from the center of mass. That's like what the center of our circular motion to the point that we care about. So that is 0.5 times cosine and sine is 60, so that's 0.25, 0.433. And then plus all this stuff, 0. Yeah, given. And so this is negative 0.433 alpha 2. Oh, thank you. I skipped one. So it's this circular motion stuff. I did that first red circle, but I didn't add on A2. Yes. And so all these together, you get negative 0.433 alpha 2 plus A2x is the x component. And the y component is positive 0.25 alpha 2 plus A2y, and the z component is 0. So our constraint equations, equation 5 star, we get from setting the x components equal. So negative 0.433 alpha 2 plus A2x equals 0. And then equation 6 star we get from setting the y components equal. So if you set them equal, that's this minus this is equal to 0. So 2 alpha 1 minus 0.25 alpha 2 plus A2y is equal to 0. Yes, indeed it should. Okay, any questions about that first constraint? So remember, we have a system of 7 equations for 7 variables is what we're looking for. So we need that other constraint equation. And the other constraint says that at C, there can't be any vertical acceleration. Or, in other words, the y component of AC is equal to 0. So the acceleration of C relative to the ground is equal to the acceleration of C relative to the center of mass of 2, plus the acceleration of the center of mass of 2 relative to the ground. And again, that's A2, and that's from circular motion about the center of mass of 2. So the acceleration of c relative to the ground is equal to alpha 2 crossed with r that goes from the center of mass of 2 to c, or for some reason the way I've been writing it is r 2c from the center of mass of 2, plus this stuff, that's 0, plus a2. And so this time, what's r? Staying alive, staying alive. Yeah, this one.
So is that your art class?
Disco?
Disco?
Yeah. Yeah, right. My college had a disco class. No, not really. That would be funny. I mean, how old do you think I am? I went to college I graduated from college in 1995. It would have been like a grunge rock class, like Soundgarden and stuff. Yeah, that's Seattle Pride. Your Seattle Pride talking. So acceleration of c relative to g is equal to 0, 0, alpha 2, crossed with negative 0.25, negative 0.433, 0, plus alpha 2, a2. And that's equal to positive 0.433 alpha 2 plus a2x, and then negative 0.25 alpha 2 plus a2y, 0, I guess. And now remember that the constraint we're looking for just says that pin can't accelerate up or down. It can't jump out of the slot. So it's the y component that we want to set equal to 0. And so our seventh equation says negative 0.25 alpha 2 plus a2y is equal to 0. Any questions about that one? It would have been like this.
And I feel the time's a ways to go. Amen.
So is it raining in your bedroom? Yeah. Okay. Yeah. We listened to a lot of grunge in those days. Stone Temple Pilots is good. Oh, that's funny. They can't let it go. Remember when everybody liked Seattle? Any other homework questions? Yeah, I am. And we probably don't have time to really work on that project problem anymore on the board anyways. I think the different groups were probably pretty different. After linkages, the best topic in this class, possibly the best topic in any class at Normandale. Calculating the motion of particles if your coordinate system is not inertial, if your coordinate system is rotating. Yes, solid state physics in a rotating coordinate system. That's a good question. Yeah. So here's the next topic. It has to do with rotating coordinate systems. And you can only use Newton's laws if you have an inertial coordinate system. So that's a good question too. So let me, Newton's laws only work in inertial coordinate systems. Non-inertial coordinate systems, the ones that give us problems, occur in two ways. The origin is accelerating. And this is relatively easy. You use relative motion for this. Yeah, I didn't even mean that one. Relative motion. That one's easier to deal with. But the other way you can have non-inertial coordinate systems is if the axes are changing orientations. In other words, rotating. This we've already done. This one is, you know, what we're getting to. And some applications. Yes, yes. But if it's Mike's banana. So first of all, you would use it if, and planets is an example of this. You just don't always get to choose your coordinate system. If you think of a coordinate system as being like a video camera, you know, where you're taking measurements, you don't always get to choose where it's mounted. You know, sometimes you just have to mount it to something that's rotating. Sometimes. Well, the easiest example is, you know, the Earth is rotating. It's not rotating very fast, so for almost all calculations, you can pretend that the angular velocity of the Earth is 0. Like, what's omega for the Earth? Yes, very good. So figure out how many seconds there are in 24 hours, and omega is 2 pi over that number of seconds. It's a tiny omega, you know. So it is rotating, but there aren't too many calculations that are so sensitive that you have to worry about that. But it is rotating, and so you'd like to mount your camera to an inertial coordinate system, but obviously it's, you know, that can be cost prohibitive or whatever to go out to space to mount your camera to measure stuff, you know. Oh, I don't know. It's sort of a theoretical thing, you know. Yeah. Shack. Yeah. Well, all prominent scientists before 1500 said that. But I don't think there have been many since then. Yeah, that's true. Yeah, Newton knew what was going on with the planets. He was in like around 1700. Okay, so that's one application. Another application is, well, that's a whole set of applications. That's the biggest chunk of it probably. Like sometimes there are just convenient places to mount your camera and you got to deal with the data you get, you know. But the other thing is if you have superimposed simple motions, so simple motions superimposed on one another, on each other. Like for example, if you had, I think this looks very similar to a problem we're going to do. So if you have one beam and it's rotating like this, and a second beam is connected to the first one and it's rotating out of the page, can you picture what's going on here? And you're trying to figure out what's happening with this point here. Those are two simple motions. You know, it's just the circular motion at this point, a circular motion at that point. But it might be sort of surprising to find out that you can't just do that with relative motion. If you just think of it as adding two circular motions together, you get the wrong answer. And the reason has to do with the fact that as this thing moves, the axis of rotation of this thing also moves. So what you do is you put a coordinate system here, mounted to one rotation. You know, you separate it into the thing that's being ridden and the thing that's riding it. Fix your coordinate system to the base thing, the thing that's being ridden. Calculate them. So if you have a coordinate system like this, then even as this thing's rotating to this coordinate system, it just looks like that circular motion. That's easy to calculate. And then you deal with the fact that your coordinate system is rotating, and you can do, you know, obviously to try to figure out, like, oh, it's going to be the cosine of this times the sine cosine. You know, it would be like impossible. But to break it up into two simple motions like that is easy once you get this idea. Yeah, and then, so the thing with linkages is just that since everything was happening in one plane, their axes of rotation weren't changed by the fact that the other things were moving. So the problems we'll do here are like, one of those things is rotating around an axis that keeps changing in time. And we'll use this approach to deal with it. Most of the time, it's just going to be at a given instant, but you could use this for functions of time. Most of the time, it'll just be like, this instant, omega is this, alpha is this, blah, blah, blah. What's the acceleration of this point? Yeah, we're going to learn how to deal with it. Any other questions about that? It's the most mind-bending part of this class. Like this? Like number 2? Well, you know, I don't know. Well, biomechanics. I mean, I guess I always come back to that. Like that could easily come up. This idea also you need to understand in order to do 3D dynamics problems. Yeah. So this idea is important when you go from 2D to 3D problems. Like notice with our linkages and rigid bodies, all we've done is 2D. Sometimes that's just out of convenience. You have to stop somewhere. But in dynamics, that's actually a very important distinction. There are big changes that come when you go from 2D to 3D, and it's because you have to use this idea to go to 3D. I haven't decided yet. We're going to do one topic after this. I think instead of going to 3D, we're going to do vibrations. Yeah, I mean, just like an introduction to vibrations. I think that'd be better. In the past, we've done 3D instead as a last topic. So, okay. Have a good weekend. Oh, man.